Hello again. This is Math 0465 for summer of 23 coming to you from the College of DuPage, and the title of this lecture is Section 0.2, Keeping It Real, Types of Numbers and Rounding. As always, please be attentive while watching this video. Calculating pay based on an hourly rate often involves rounding numbers to amount more easily used in calculation. And these can be policies or due to the software being used. But how time is rounded can have an impact on how much an employee gets paid and how much the employer has to pay. So here I'm asking you to round each amount of time in the table according to the rounding rules provided, and calculate the total number of hours worked in this week for each of those. And you can see this looks like a nice application of Excel, and it does. You're also supposed to answer which rounding rule is best for the employees, which rounding rule is best for the employer, and why did that rounding rule favor the employer for these particular times. Now I'm asking you to pause this video, work the problem using Excel preferably, and then come back. Let's come back and see how you did. Again, I used Excel to enter a bunch of text for the headings and also for the hours on days. But then what I did is I did the rounding by hand. So 5 hours and 20 minutes, if you round to the nearest hour, that's closer to 5 than it is 6. These other three are closer to 6 hours. So if you round to the nearest hour, what will happen is you get 5 and 3 sixes, and that will add to 23. But I didn't add this by hand. I used the Excel function. So I went up to the Excel bar and I clicked on the f of x. And then I looked for, searching for functions, I looked for sum, which allows me to add things up. So I clicked on sum, and this is sum, and then I put the numbers or the cells in that I have. So I click this and I get equal sum with parentheses, but then I drag and drop. So I go up and I drag and drop B3 through B6, and then I hit enter, and I get 23 for this Excel value. You should make sure that you can do this. Now if I round to the nearest hour, but now I'm rounding up to the nearest hour. And so this is going to be 6, 6, 6, and then it's 7. Now it was only 3 minutes, but still I'm rounding up, so I get 7. And then what I'm doing is I am going to grab a hold of this and pull the formula across. And so when I do that, I will be adding these, so I get 25 for this one. Now if I round to the nearest quarter of an hour, that will be 0.25, 0.5, 0.75, or 0. And so you see, when I round to the nearest hour, 5 hour and 20 minutes is closer to 5.25 hours. This is closest to 5.5, this is closest to 5.75, and this is closest to 6. So when I add those together, I get 22.5. And then if I round to the nearest half hour, the nearest half hour is going to be 5.5, 5.5, 6, and 6. So I get 23. Again, I'm dragging the formula across using the sum function. So if I look at this, which rounding rule is best for the employees? Well, the one that gives us the highest value. So rounding up to the nearest hour, not surprising, gives you the best value. Which one is best for the employer? Well, if they round to the nearest quarter hour, they will get they won't have to pay for 22.5 hours. So that's best for them, and it had to do with the numbers and the way they rounded, and we've proven why those rounding rules favored the employee for those values of hours. It will change depending on what are the hours that are clocked. Now, this causes us to think about numbers, and so we'll talk about real numbers. The set of real numbers includes all the numbers that can be represented on a number line. So for example, 3, 0, 1/2, minus 5.7, and pi are real numbers. You can draw those on a real number line. The set of real numbers contains the following sets of numbers. So we have the set of counting or natural numbers, which is the set containing 1, 2, 3, and so on, an infinite set. And this is used to count objects. There's another set called the whole numbers where we add 0, and this contains the counting numbers and 0. We then have a set called the set of integers, which has the whole numbers, but also the negative of the counting numbers. And so this includes this infinite set where we allow negatives, and that contains the whole numbers and their opposites. The set of rational numbers contains numbers that can be written as a quotient of two integers. Now, you can think about this as being fractions, I guess, but it could be positive or negative. And decimals that terminate or repeat are rational numbers. But there are decimals, and examples of those that terminate and repeat are 2/3, that would be 0.6 repeating, minus 3, 1.2, 4.5 is 4.5, 0, and 0.3 repeating. But there are numbers that neither terminate nor repeat. So the set of irrational numbers contains numbers that cannot be written as a quotient of two integers. Decimals that neither terminate nor repeat are rational numbers. And examples include the square root of 5. In fact, the square root of any prime number will be a irrational number, pi, and this number never repeats because we keep going further and further out. To look at this another way then, the counting numbers are contained in the whole numbers, are contained in the integers, are contained in the rational numbers, are contained in the real numbers. But the real number line contains both rational and irrational numbers, and these two sets do not overlap. Repeating some earlier comments, rational numbers have terminating or repeating decimal expansions, but irrational numbers, decimal expansions, neither terminate nor repeat. Here's a problem for you to do. Please pause the video, read it, and we'll see how you do. Let's see how you did. An example of an integer that is not a whole number is minus 5. There are many correct answers to this problem. A rational number that's not an integer, an example of that would be 2/3. There are many correct answers. There's only one answer to problem C, listing all integers between minus 10 and minus 5 inclusive. It is these. And again, notice the endpoints are included. D, you're to list all integers between minus 10 and minus 5, but you don't include the endpoints. State an integer that is also a counting number. There are many answers to this, but 5 is one of those. And write a decimal that is irrational other than examples provided. Well, I told you earlier that the square root of any prime is irrational, and so the square root of 2, of course, would be one example. Now, the real number system is positional, and digits have different values depending on where they are placed in the numeral. Place values differ by powers of 10. So moving one step to the left always is multiplying by 10. Moving one step to the right is always dividing by 10. So each place value gets 10 times larger as we move left and 10 times smaller as we move right. Place values are named starting on the left in groups of 3 separated by commas often. So these are ones, tens, and hundreds. This is 1,000, 10,000s, 100,000s. This is 1 millions, 10 millions, 100 millions. This is 1 billion, 10 billions, 100 billions. This is 1 trillion, 10 trillions, and 100 trillions. And it does keep on going. So these are your place values. Let's do an example. So please read these problems and do the rounding as it says. And so round each number as requested. I'm going to pause the video. And you should too. Let's see how you did. If we round this to the nearest 10, we will get 910. If we round this to the nearest 100, the 100th place is here, so we're rounding up, but that makes this round, so that the nearest 100 is going to be 2,000. And rounding this to the nearest 10,000, this position right here is 10,000. 6 is more than half, so we round that to 2,280,000. So to round whole numbers, you identify the target digit in the requested place value position. Look at the digit 1 position to the right. If this digit is less than 5, the target digit will remain the same. If the digit is 5 or larger, we'll increase it by 1. Replace all digits to the right of the target digit with a 0. So we round 15,489 to the nearest 10, we get 15,490. Rounding that same number to the nearest hundredth, we will get 15,500. To the nearest thousand, you see we're less than half here, and so that is going to be 15,000. And to the nearest 10,000, this is 20,000. So here's a problem for you to do. You're supposed to take this number and round it to the nearest place there. So please pause your video. Let's see how you did. Well, rounding this to the nearest 10,000s, this is the 10,000ths position, so we're going to go to 70,000. To the nearest thousandth position is going to be 67,000. To the nearest hundredth position, it's going to be 67,300. And to the nearest tenth position, it's going to be 67,260. Now, in some applications, it makes sense to round your numbers up or rounding down, and it really doesn't, and not necessarily round to the nearest number. So you always want to follow directions. So when instructed to round down, you keep the target digit the same or lower it by 1. When instructed to round up, you keep the target digit the same or increase by 1. Here's a problem for you to do. Round each of these numbers as requested. Please pause the video and give this a go. Let's see how you do. So if we round this down to the nearest 10, we're rounding down, so we take this down to 340. If we're rounding this up to the nearest 100, you go to 900. If you're rounding this to the nearest million, it's going to be, we're rounding up, you round to 4 million. Now, not all numbers are included in the real number system because there are numbers that are called imaginary numbers, and they're expressed using I for the square root of -1. And imaginary numbers are part of a number system called the complex numbers, which has the form a plus bi, where a and b are real numbers. Now, this book will focus on real numbers, but you might encounter those later in some course. So here it says use your calculator. I'm suggesting that you use Excel to find the value of the following square roots and state your results on the calculator and classify each answer as rational, irrational, or imaginary. So here's the problem. This means square root of 9. Those are all square root symbols. So I'm going to ask you to pause. And now let's see how you did. This time I'm clicking on the function button here in Excel, and I'm calling up a function that is called the square root. And this is a square root function. Now, when you click on that, it gives you an equal with the square root, and what we're going to do is we're going to point and click. So to get the square root of 9, I use the square root function here. I say, okay, that's the square root of a number, and so this is going to say equal square root with a blank, and then I'm going to go and I'm going to click on this 9, and when I hit return, it will give me 3. And then I'm going to pull this function down, and it will give me these numbers. Again, you should verify that you do get these numbers. And this is a rational number. This is an irrational number because it includes a factor, a square root of a prime number. This is a rational number because it is infinitely repeating, this gives you a not real number. So practice pulling the functions down, and again, that's an imaginary number. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself because self-care is important, and of each other because you're all in this together. Stay on the road. There's a bright future ahead. God bless you all.